Hello everybody, I wish you're doing well. Today we will do a new functionality of CATIA V5, that is static simulation. So we will take an example of a workpiece that is here. It is in a step format, and we will do a simulation. So here is our workpiece. So this is it. Then we will create a folder. New folder, we will call it simulation, and we will open it. We will use it in the video. So we have here our workpiece, then we have here apply material. Here we can apply any material we want. This time I will choose aluminium, but I will show you the others. So we have a lot of materials here, and we have construction materials, for example. Here we have fabrics, we have leather, we have carpet, we have honeycomb, for example. Here we have metals, as we see. We have others here. We have paintings, we have shape review, we have stones. Oh, these are stones. Here we have the woods. And so, as I said, we will use metal, like aluminium. When we click with the right button, we can see the properties. And here are the properties. We can see here all these, but we can't change them. So this is it. We have the here texture, and we have inheritance here. We can change the name. Here we have analysis. It is here the what we will have to use today in our analysis, in our mechanical static simulation. We can choose here the type of material. If it is isotropic, in general, isotropic means that the material have the same properties in all the directions. For example, in X direction, if we do traction test, it will be the same in the Z direction in the materials. If we do traction, for example, in the X and Z and the Y, it will be the same material. For orthotropics materials, it is, for example, for composite materials, it has, for example, uh, uh, in 2D, it has, for example, how to say it, yield modulus in Z direction, and another one in Y, and another one in X. But here orthotropic for 2D, it has just two different, and it has Poisson's ratio in every plane X, Y, X, Z, and it has also share modulus in any in all the planes. So this is it. We have here, for example, fiber materials. Fiber materials, it is composite materials, but in fibers, not in as in orthotropic. It is mesh diff. I can say it like this. It is in a leather, for example. Here we have for honeycombs, it is honeycombs something to have a better uh, resistance for flexion. We use them in general in planes. Mm, so in place for the to have a good resistance to uh, flexion. So this is it, honeycomb. Here we have orthotropic, but in 3D, same as orthotropic for 2D, but with a third direction. And here we have anisotropic materials that is not isotropic. It has young modulus and shear modulus in every direction. Here we can do it for it is for the the CATIA module of composite materials, and here it is for the drawing. If for example, for composite materials, we'll return into analysis. So we'll say that it is isotropic material, and for aluminum, or this aluminum of this example, it has these properties. It has this yield strength, this thermal expansion, this density, this Poisson's ratio, this Young modulus, and in general, Poisson's ratio is between 0.2 and 0.4. In general, it is 0.3. So this is it. So we can change these parameters, for example, for another type of aluminium. But to put this material into this workpiece, we can drag it directly like this. We'll apply it and press on OK. Then now we can open our module of simulation. It is Generative Structural Analysis. Oh, this is it. We can do frequency analysis. We can do free frequency analysis. But now we will do static analysis. We'll say press on OK. Now we have this workpiece of aluminum because we have choose the aluminum. So now we have to block some directions or some movement. So to do this is it is the boundary conditions in static simulation. So we can do a clamp, we can do a surface slider, we have a slider, we have sliding pivot, we have ball joint, we have pivot. These are all constraints, if we can say it like this, but so we can put and block some directions. Here it is user defined restraint, and here we can put an isostatic restraints. In general, I like to use clamps, so let's put it here and put on OK directly. This is just an example. So this is it. We will block this direction, and here we have the force. Here we have a pressure, for example, for tubes. We can do pressure for fluid simulation. Here we have a distributed force. Here it is a moment. Here we have bearing load. Here we can import forces and moments. Here we can put acceleration or gravity. Here we can put a rotation force. And here it is enforced displacement, so we can choose our boundary conditions. We can put enforced displacement, for example, if we want to put our boundary conditions as a displacement. And here we have the temperature field if we want to put thermal conditions. And here we have combined louds, and here we can assemble louds. So this is it for this for what we will learn today. So I will put distributed force. I will put it here, and let's put, for example, for this example, let's put 10 10 meganewton. So let's see. Let's press on OK. And now we can calculate or compute here. We have also this compute with adaptivity, but in general we use compute. So we put on all. Now it will do its calculus. So it will take 6 seconds of our CPU, and this number of kilobytes of memory, and this number of kilobytes of disk. So we will press on yes. We'll do the calculation. So it finished our calculation. So now we can see the deformation. So this is our deformation. And here we can see the von Mises stress. So von Mises stress is just a convention to calculate this stress. Here we can put displacements. Here it is principal stress, and here we have the precision. So this is it. So this is what we can do with this simulation module. So this is it. And here we can open this to see our clamps, restraints, and clamps here. We can see loads here, the forces that we have put. And here we have put a distributed force as this. And we can, for example, change it here. Let's put it in compression. Let's put it and let's recompute. And let's see what will happen. So we'll have a compression as you can see it. Let's try to put more force. Let's put 2.0 here. And let's recompute. So it will give us this, but it is not our real form. Yes, because we have put a lot of force. Let's recompute with another realistic force. Let's put 11 here. If it can, it will. No, it is not realistic too. So this is it. Let's put something else. Let's return to. Let's put a small or a really small force. Let's compute it. So here's what we have with a small force. Let's see the colors. We have not a lot of deformation. So let's add a 0 here. Let's calculate it. Same thing, not a lot of zero. Let's add two of zeros. Same thing, no lot of displacement. Let's put a zero here. Maybe now we will see some deformations. Same thing, no deformation. Now we can see some deformation here. You can see it. Let's see it like this. So we have some deformations. To return to our phase, let's put double zero here. Not realistic. Just put 10 here. So this is our deformation for this. And now we can have the reports from here. We can export here the report. Here we can generate a report. We can choose where we put it here. And let's put it in our folder. We call it simulation. So let's press on OK and let's save it. So here is the report that we will have. So here it is. And here what we will have, the deformed mesh and all the data. We will have data here. So this is it. And to have the detail, we can export the data. This data we can export it in 3D XML files for deformed mesh. But this in reality, we won't have something that we can use. So let's see it. Let's see what we will have. It will take time to have it. So data mesh, we will have these informations, number of nodes and number of elements. And now when we export I don't know what it doesn't want to be exported, but in general we can export it. So now we can export these files. Here we can export it as text file, 3D XML file, or Microsoft Excel worksheet. We can export it as this. And now we can find it directly here as a Excel worksheet. And we'll find all the coordinates here and the values. So this is it for every node. So this is it. And with the same technique, we can export transactional displacement. So we can't export it because it is deactivated here. So we can activate it and export this data. So we can rename it here. Let's put just a 2. We can export it as a text file or Excel worksheet. Will take time, so you can take the data and you can analyze it. So it is here. So these are the results. You can find them here, and you can analyze them if you are uh, calculus engineer or structure engineer. So this is it. We can export data, or we can, for example, export the report here. So here is the report that we will have, or we can export it here as Excel worksheet. Let's name it 3 here. So it will take time. So this is what you will have. Here are the data. And for the estimated error, same thing. You must activate it and export this data as 4. You can deactivate it here or hide it. So this is it. This is everything. You will find it here. So here are the errors. So this is it for the simulation. We have static case. We will do the vibration case next time. And this is it. Thank you for watching and see you soon.